Hi, this is Fahad Labid. I'm a chemical engineer major and a procurement lead for this project. Welcome to our project, Utilization of Mealworms and Black Soldier Fly as a fish meal replacement in commercial fish feed. Let's start with the big picture. Global fish demand is expected to double by the year 2050 due to population growth and the need for a reliable source of protein, especially in developing countries. Aquaculture is meeting this demand. However, traditional fish feed is expensive and unsustainable because it relies heavily on fish meal, which is contributing to overfishing, damages the marine ecosystem, and raises production costs. For small-scale farmers in countries like South Africa, the price of fish feed is a major barrier. That's where our projects come in. We're addressing two key problems, which is the environmental impact of traditional fish feed and the limited accessibility of affordable, high-quality alternative for small-scale farmers. So our goal to develop fish feed that is nutritionally comparable to the traditional fish feed, aiming for 32% protein content, as well as affordable for small-scale farmers, and finally environmentally sustainable by using an insect-based protein. To do this, we created and tested 18 unique feed formulations using mealworms, black soldier fly, larvae, and a blend of both, and we evaluated them based on buoyancy, water stability, and protein content. By the end of this project, we aimed to find the optimal insect-based fish feed that small-scale farmers can adopt easily using local resources while reducing both cost and ecological impact.
I'm Adrian Jimenez, and environmental engineering major. I'll be talking about our experimental setup, design, procedure, and data collection. For our experimental setup, we primarily used common household kitchen tools or utensils. This kept the process simple, accessible, and easy to replicate. We first ran a small pilot experiment to confirm everything worked, then moved forward using the same setup for the full experiment. We began by preparing the insect powders. Mealworms were defrosted, then dehydrated for a full day using a food dehydrator and ground into a fine powder. Black soldier fly larvae required no dehydration, just grinding to achieve a similar consistency. Each formulation included insect powder, cornmeal, gelatin powder, canola, oil, and water. We created 6 formulations for each insect type, one with black soldier fly, the other with mealworm, and a third using a 50-50 blend of both insect bases. Once the powders were ready, we measured the dry ingredients, added water gradually, and then hand mixed until well combined or coagulated. We used a meat grinder with a pelletizing attachment to form pellets, then dehydrate them again to complete the process. To test performance, we placed the pellets in water to simulate feeding conditions, mainly focused on buoyancy and stability. For buoyancy, we placed a set number of pellets in water and counted how many floated every 15 minutes over 1 hour, stirring throughout. The higher the average number of pellets floating, the better the ranking. For stability, we added 5 grams of pellets to water for 2 hours, stirring every 30 minutes. At the end, we removed and dried the remaining material and recorded the mass loss. Lower mass loss meant higher stability. We used Minitam to guide our formulation design and evaluate which ingredients had the greatest impact on performance, helping us refine the ingredient ratios and repeating the process to select our best formulation.
Hello, my name is Trisha Jean Lane. I am an environmental engineering major and the team lead for this project. Now that we've covered our materials and methods, where we tested combinations of black soldier fly, mealworm, cornmeal, canola oil, gelatin, and water, let's move into our findings from the data analysis. Using Minitab, we ran scatter plot screeners to evaluate how each ingredient affected key pellet properties, water stability, and buoyancy. For water stability, black soldier fly and mealworm showed the strongest effects. Black soldier fly had a positive quadratic relationship where higher levels significantly improved pellet integrity. Mealworms had a negative quadratic trend where mid-levels reduced stability, but higher concentrations helped recover it. These ingredients also had the highest R-squared values, meaning they were the best predictors for pellet stability. For buoyancy, cornmeal had a negative linear impact, reducing flotation. Gelatin had a mild positive effect, possibly by improving pellet structure. Other ingredients had minimal influence. Based on these insights, we selected our final formulation, Black Soldier Fly Formulation 1, with Black Soldier Fly at 33.9%, cornmeal at 19.7%, canola oil at 6.6%, gelatin at 6.6%, and water at 34.2%. This blend ranked highest in water stability, offered moderate buoyancy, and achieved a protein content of 30.9%, which is slightly below our 32% target. Still, it represents the best balance of nutritional value and physical performance, making it our most promising formulation for fish feed development.
Hi, I'm Bobby Luna. I'm a chemical engineering major student. I'm going to give you a quick breakdown of the costs we determined for both small-scale and large-scale fish feed operations. Starting with the small-scale setup, this model is designed for individual farmers or smaller communities. We kept the equipment affordable and easy to use: a small dehydrator, grinder, and hand mixer, manual pelletizer, and some basic packaging tools. All in, the equipment costs stay under $5,000. Weekly production is around 20 to 30 kilograms of feed, and the cost to produce each kilogram is roughly $1.27. That includes electricity, labor, and ingredients like dried black soldier fly, which run about $2.50 per kilo. This setup is simple, flexible, and ideal for farmers who want to stay self-sufficient. Now for the large-scale system. This is designed for commercial production. It includes industrial-grade gear, 3 100 cubic meter storage silos, a high-capacity mixer that handles 15,000 kilos per hour, 6 pelletizers, a rotary dryer powered by a 4,000 kilowatt heater, and a volume blower and packaging system. This line runs 8 hours a day, 250 days a year, and can turn out about 20 million kilograms of feed annually. While the upfront investment is significantly high, in the hundreds of thousands of dollars, the cost per kilogram drops way down. Using black soldier fly meal, the overall feed production cost is estimated at less than 85 cents per kilogram. That's a big efficiency gain thanks to economies of scale. In short, the small-scale option is affordable, accessible, while the large-scale operation is built for serious volume and long-term cost savings, especially for commercial use or cooperative farming models.
In conclusion, our project shows that insect-based fish feed can be a real solution to some of the biggest aquaculture challenges today. It's affordable, more sustainable, and still provide the nutrition fish need to grow.
With simple tools and data from our experiments, we created a strong formulation using black soldier fly that held up in water, floated reasonably, and came close to our 32% protein goal. We also compared small and large-scale production costs, showing that this feed works for both individual farmers and commercial operations.
Next, we plan to test how fish feed actually respond to our feed and continue refining our ingredients to reach that full 32% protein mark, while also improving how well the pellets float and hold together. We'll also monitor water quality in future trials to make sure our feed support healthy aquatic environments.
Before we close, we want to sincerely thank Andrew, Justin, and Efe for their hands-on support, as well as Dr. Kim Ogden and Dr. Adriana Brush for their mentorship and guidance. And a big thank you to the Chemical Engineering and Environmental Engineering Department for making this research possible. Thank you for watching.